Hello, everyone. Good morning, good evening, good afternoon from everywhere you are. This is Mohsen from Microsoft Zero to Hero. I'm so happy to be here with another great session. Before the kick off the session, let me share some slides with you about the community and the future program. Today we have a James who wants to talk about document data extraction with Azure AI. The topic is very interesting, and as you know, we are a part of Microsoft Learn community. Microsoft Learn community is a central hub, a lot of learning content. You can choose your learn content based off your role, based off the certification, and actually from this link https://ak.ms Microsoft Learn community, you can join. You can ask your question from a lot of learning experts. Actually, this is a Zero to Hero October calendar. We are a lot of great sessions in the future. All previous session uploaded in our YouTube channel. You can watch again. And this is a amazing November. It's women intake. Please register and reserve your seat for November. And then the last slide is our code of conduct. Be aware of other, be friendly and passionate, be welcoming and respectful, be open to all question and viewpoint, be understanding on different, be kind and considerate to other in the chat, in the voice, and so on. And time is to add James in the stage. Hello, James.
Hey, everyone.
Hello. How are you, James?
I'm good, thank you. And yourself?
Fine. Thank you. Great. Thanks you for accepting and for this session. And we can start your session. Before you start your session, just for your information and other participants, end of the session, we can select the best question as a winner for Microsoft Exam Voucher 50% and Fundamental and Advanced Exam. Yeah, let me add your presentation in the stage. You can start.
Cool. Thank you.
Yeah.
All right. Hey, everyone. It's exciting to join the Zero to Hero community today. My name's James Croft, and I'm a software engineer at Microsoft on the Azure CXP ISV and startups team. I work every day with startups and solution providers who are pushing the boundaries of AI, and I help to guide them on how to optimize their Azure AI workloads and land them successfully on Azure. Today, what we're going to look at is how you can use Azure's AI services to accurately and confidently classify and extract structured data from any type of document. Everything that you're going to see today is based on establishing new ways to work with AI, and specifically generative AI, to simplify document processing. So let's jump into it. I've got two main learning objectives for you today. First, I want to put things into perspective because it's important that you understand the challenges that people face with document processing today, both from the perspective of real-world processes, as well as the technical challenges with traditional AI and machine learning approaches, specifically for solution providers. Then we're going to spend a fair amount of time in code, and I'll show you various techniques using Azure AI services that both solve and simplify those challenges. All of these demos are going to be run live, so I'm hoping that the demo gods are with us. So when it comes to fundamentals, there are two main challenges at the core of extracting data from documents. The first is document layout. I want you to think of some invoices that you've ever received for goods or services that you've purchased. They often tell you which items that you've bought, how many, the price, and maybe even the total cost. But how many of them actually look the same? Then we've got the data. Invoices, they usually contain well-structured tables, and they might have specific elements like company names and company addresses in consistent places on the document, But if you think of a contract, for example, these usually contain huge blocks of natural language, such as terms and conditions, which may even include rules about data, but perhaps don't provide the specific values in the document. If this was a 20+ page document, you'd need to go through the entire document in detail, reading and understanding the text just to extract those key pieces of information. Now, imagine that this is your job, to go through manually reviewing and extracting data from documents. Interestingly enough, there are companies that still do this today, and it's incredibly time consuming, but they're looking at ways to speed this up with AI. Now, if your background isn't naturally in AI and machine learning, the idea of having to build your own custom vision model for processing documents can be quite daunting. You need to get your hands on a decent training data set, understand how to label each of the documents, build the custom model for each document type, and then manage them throughout their life cycle, which includes updates as document layouts evolve. This happens over time, and these are unknown to your model, so you need new data. Even just acquiring that initial data set is a challenge. We know that many people don't want their data being used for training purposes in AI and machine learning models. So imagine being an AI startup, for example, which is building a document processing technique where customers don't want their data used in their model. It makes it very difficult to provide a service that offers accurate results. It's also more common than not to process more than one type of document. Imagine that you're working in the legal sector and your job is to handle a legal case which contains documented evidence. This could be a report, a diagram, handwritten notes, letters, and even emails. They're all bundled together. There's no specific order to them, and you have no idea what is in the bundle that you're being given. It's your job to go through these documents in detail, ensuring that they meet some validation criteria to prepare that evidence for court. Here, it's no longer a job of just extracting data, but to first classify what each document is. Then, when you start applying AI and technology to solve these problems, people want them to reduce the overhead of doing that task manually. You want to achieve a high degree of automation, being confident that that system can operate with a minimal human intervention. They also need to be highly accurate. For some use cases, like that legal scenario, the approach needs to be achieving 95% plus. And we know that AI systems aren't 100% accurate. This is why we need both the confidence in the system, which we can get from most models, to determine whether to escalate this document to a human for review. And there's also the expectation that by reducing the manual overhead, that these AI-based solutions will be much quicker than a human at deciphering the data within a document. We're not expecting immediate responses, but maybe a few minutes max per document. So with those challenges in mind, how can AI services in Azure help to ease those challenges? And the best way to show you is to get hands-on with code. What I've prepared today is a collection of samples to walk you through various techniques for classifying and extracting structured data from documents, providing comparisons between each technique. They build on each other as they go along. I'll work with some no-code, low-code tooling, as well as some Python examples as well. And these will just help to understand the benefits and drawbacks of each approach and set you up for success, taking them and adapting them to your own specific needs. So the first thing I want to show you is a low-code solution in Azure AI Studio. This is a new feature of AI document intelligence called document field extraction, which is currently in preview. These can also be built with code. Behind the scenes, there are components of the schema, the data, the OCR, and the layout analysis for each document. But I'm going to show you how to do this with the low-code technique. So the way this works is you define a schema. This schema is fairly simple to implement within the UI. There are some limitations on nesting and defining reusable objects in the specific schema, but what we can do here is define what the extraction is going to look like. So we have a few fields. We're going to be processing an invoice as part of this specific sample. This invoice is 2 pages, fairly straightforward. One is the invoice itself, and the second page is returns. The reason I'm using this example is because the UI for this invoice is somewhat complex in that it's a quite complex grid system with merged cells. We also have some handwritten signatures, handwritten names, and also there's some key pieces of information that we'll want to extract, which are covered by handwritten text. And then on page 2, we have a table structure here where we have a reason which is across multiple lines. And the reason I want to show this is as we progress, you'll see how we can use different techniques to improve each time. So we define our schema. The schema is each of the fields that we want to extract and a description for that specific field. Behind the scenes, these documents are then auto-labeled using GPT, combined with AI document intelligence's capabilities to locate and highlight key pieces of information on each page. If we go to the labeled data, you can see this schema mapped to the document that I previously uploaded. Here it's predicted all of the values and extracted them so that I can then use them in a downstream process. On the right-hand side, what you're seeing is a confidence score. The confidence score for AI document intelligence is how confident it is that this is the right piece of information in the right location. And there may be examples where it's not quite correct, or that the value itself is not correct. So what we can do here, we can improve the model that we're about to build by correcting the data. So for example, in our product signatures, we have, in our return signatures, it has detected that the type of signature for the second person has not been picked up. So we can edit this. We can select what the type is. In this instance, it's driver. Here, it's actually selected the wrong thing as well. It's selected the customer up here. So we can correct this and select customer down here for this specific value. And we can also erase these values because they're also incorrect. Now that we're happy with the changes that we've made, we can then build a model based on labeled data. If we wanted to, we could also add more files here. The labeled data is not our test for the model. The labeled data here improves the model's accuracy when it's extracting data. So once I'm happy with this model, I can then build this. I can give it a name. So in this example, I'm going to call it invoices version 1.0. And behind the scenes, this is then going to start creating a model that's specific to extracting invoices. Now, while this is still creating a model per document type, the way of building the model is much easier with this document field extraction technique. And once we've built our model, we can test it. So we have our schema defined and we have our object structures. So if I go into test this now, I can upload a new file. If I go to my training data, I can upload invoice 1. Invoice 1 in this specific example is a different invoice structure entirely, but contains the same kind of data. So we have the invoice products that we're purchasing, and we also have our invoice returns as well. And if we run the analysis on this document, if the demo gods are with us, what we should see is an extraction and confidence scores for this specific test. So here, it's accurately extracted the customer address, the customer's name, the delivery date. And also all of these values have been extracted using generative AI behind the scenes in combination with AI document intelligence. Now, I want to point out specifically what the confidence is actually for and where it can be useful in a specific extraction. So the confidence score comes with every single request that you make. It's an internal assessment that the model runs on how certain it is about the predictions that it's made. And this can be a great indicator for whether to move to a manual verification by introducing this human in the loop approach. So say, for example, the majority of the confidence scores here are quite low. Say it's below 70%. We can then escalate through our application that we build with this specific technique. We can escalate to a human for review. When both the accuracy and those confidence scores are high, that is the perfect place to be in. But in practice, you'll always incorporate that confidence score into that decision-making process. So next I'm going to jump into code, and we're going to take a look at ways that we can implement Azure OpenAI in combination with different AI services in Azure as well. So we're going to take that same invoice example that we demonstrated in document intelligence. But because now we're working in code, we need to define a model for this specific document. So we create a Python data transfer object. It's a model that represents what we want to extract. Behind the scenes, we're also using the Pydantic library in Python, which will take this model and generate a valid JSON schema for the invoice model that we can then use in our requests to the generative AI services, the language models. So the first approach that I want to show you is using Azure AI Document Intelligence and Azure OpenAI's GPT-4o model to process a document and extract data. The benefit of using Azure AI Document Intelligence is that it supports a variety of different file types right out of the box without any additional effort. So that includes PDFs, HTML, and Office documents. The pre-built layout model that comes as part of Azure AI Document Intelligence does layout analysis over the document itself, but it also has a unique feature where it can convert the document into a markdown structure. So what we can do from there is construct a system prompt that defines the instruction for the extraction, and then we can construct a user prompt which defines the specific document's type of extraction, which will include any intent, rules, and that markdown content. From there, we can make a request to GPT-4o using the structured outputs feature to constrain the response. The structured outputs feature of GPT-4o will ensure that the output is strictly in the format of the JSON schema representation of the invoice object, which means you're guaranteed to get the JSON object back and deserialize it successfully so that you can use it in a downstream process. And we'll do some evaluation on the output as well. And I'll walk through the code and I'll show you how this actually works. So the first thing that we need to do when we want to measure accuracy is evaluate the output. So we need to establish a ground truth, or in this specific example is our expected output. This was reviewed by me and extracted into the invoice model that we currently have based on that original invoice document. So this is my expected output. Then we can use the SDKs for Azure AI Document Intelligence to make a request with the document PDF to extract to Markdown. And then once we have the Markdown content, we can create those prompts. So the first prompt is the instruction. It's a system prompt. You're an AI assistant that extracts data from documents. It really only needs to be that simple. You can add some more domain specifics here, but the idea behind this approach is that you're building a function within your application that performs document data extraction, and it would be generic enough that you wouldn't need to change the system message. The user prompt is where you are providing the parameters, if you want to call it that in an AI system, that includes the instruction for the specific document. So in this case, extract the data from this invoice. And then we can provide some additional context that guides the model to the response. So if a value is not present, provide null, and date should be in a specific format. We then provide the markdown, as I said, and the invoice object as the response format. Now, using Pydantic, this allows this request to automatically convert that invoice model into the JSON schema, the valid JSON schema that's required for structured outputs. From there, we can start visualizing some of the data. So I want to show you this more so that you can see how it works behind the scenes and what's actually happening. So we have the markdown structure. So this is what Azure AI Document Intelligence generates. And you can see here that the structure is somewhat complex. And this was because of the complexity in the grid system. Markdown really isn't good at merged cells, for example, but it's extracted enough of the structure that will help the model understand how to process the data. Something to note here, though, is that you can also see some of the challenges starting to appear with the way that the document intelligence OCR works for specific challenges like the text that's overlapping based on a handwritten signature. So here it hasn't quite extracted the correct date, which was underneath the invoice signature here. So this is the markdown structure. And from there, we can do that evaluation. For the invoice itself, the SDKs for OpenAI will return this in the extracted format already. So you will get back an invoice object. We can then perform an evaluation of the accuracy based on comparing each of the fields and values, and then determine the confidence. Now, the way that the confidence works is Azure AI Document Intelligence will return back to you the confidence scores for each of the words and lines that were extracted as part of the layout analysis. So not only do we have the markdown, we also have the confidence from the model, which you saw previously in the UI. So what we can do from there is compare our extracted values to the data that's in the OCR analysis to work out how confident the model is that that piece of data existed within the original layout analysis. And so we represent this and I display this in a way that you can then visualize what's just happened. So here you can see that payable by could not be determined, so it returned none. And there were a few fields which weren't quite correct, as I mentioned before, around overlapping of the lines in the returns on this page 2, and you can see in this specific example where this technique has, for line 0, the first item has returned the first part of the text, and for the second item has returned the second part of the first item's reason, because it's detected that it's on a separate line. You can also see here that it's also detected that there is a signature for the driver and the customer. Now, what I want to point out about this specific capability is there is no vision analysis of the image of the document. So this is where you start to see where the confidence score and the accuracy need to be go hand in hand to work out when to escalate. Because in this specific example, we have a false positive and a false negative appearing in the result, because there is no discernible way for this model to know that there is a signature, because the signature doesn't appear in the text for the markdown extraction. So what the model is doing, what GPT-4o is doing, is inferring that because there is the signature name is there, that it is signed. So it's detected that Sarah H, for example, is the customer, and for that reason, there must be a signature, but it doesn't know that for certain. So this is just one approach, but say, for example, you weren't using GPT-4o and you were using a different model which doesn't support structured outputs. How do you achieve that same mechanism, say, for example, with Phi 3.5 mini? So it follows the same extraction scenario, but because we're not using structured outputs, we have to do more prompt engineering to create the structured output itself. So if we take a look at the way that the completion request is created, we need to expand on that system prompt. So it's no longer you're an AI system that extracts data from documents, but we're providing it the instruction for how to actually extract. So we add this additional and returns them as structured JSON objects, because that's what we're expecting. And we also add this additional piece of information: do not return as a JSON code block. If you've worked with any language model currently, what you might find is that when you request for specific things like JSON objects, that they are returned as a markdown code block for JSON, which means that then you in your application have to do some post-processing to get the data out. And you can tailor the language model through your prompts to not do that. And then again, we follow that same structure for the user prompt, extract the data from this invoice. But in this example, we're actually going to provide the JSON schema as part of the prompt. So instead of what you get with GPT-4o, where you can provide as a structured output, we're here instead providing the JSON schema as part of the prompt. And again, we can go through that same process. You can visualize the markdown. Now, if we take a look at the extraction here, this is just purely for our context using Phi 3.5 mini. While you see that the accuracy is quite high for this technique, it's sort of swayed from the open AI technique, which is using GPT-4o in terms of accuracy. It's still highly confident that it's got the right result, but the accuracy is a little bit lower. And there are ways that you can improve on the prompt engineering to improve that accuracy even further. The smaller language models like Phi 3.5 mini and even GPT-4o mini require some more tailoring in the prompt to actually get an accurate result. But you can see here that it's highly accurate in terms of, we're in that 70% plus range, but the confidence is very high on this as well. So I'm going to shift gears and we're going to take a look at a different document. So when I mentioned before that we were potentially using contracts to extract pieces of information with large blocks of natural language, there's more complexities to consider. We have a mix of structured and unstructured data. Some of that data can be easily interpreted by the table structures. However, some of the values may need to be inferred based on the rules that exist in the text, like renewal period, for example. So if we drop to the bottom of this document, we have large blocks of terms and conditions. And in here, we have this renewal period as part of the policy. 21 days before your policy ends, we'll send a renewal notice that the insurance cover is due to expire. This 21 days doesn't actually give you a value. If you were processing this document yourself, you know that it's 21 days before your policy ends. So you've had to go to page 13 to go back to page 1 to find what the current date is, the end date of the policy, and then to work backwards to find that value. But the models, there is no way for them to infer this piece of information without some additional context. And I'll show you what I mean. So we're going to take a look at the way that you can use vision techniques now with GPT-4o to analyze the document's pages. So there is a challenge here coming from the document intelligence approach, in that document intelligence can simply just process any type of supported document. But with this approach, the GPT-4o model can only process images. So developers need to find a way to take on ownership of ensuring that the documents that are provided in their application are converted to images first and then put into the request body to Azure OpenAI. If we take a look at the actual extraction technique here, I'll show you how this works. So we're using PDF to image in this specific example, but you can use any library out there which converts a document into an image of the page. So first we need to prepare the user content, because there's some additional work that needs to be done here. Again, we're processing a specific document type, extract the data from this insurance policy. And if a value is not present, provide null. And here's where we're providing the hints to the model on how it should interpret the other pieces of information, like the policy renewal. Some values must be inferred based on the rules defined in the policy. Providing that instruction in the prompt will ensure that the model focuses on values which do exist and other key pieces of information that are inside the document. And again, date should be in the format. From there, what we do is we process each of the document pages. So using PDF to image in this specific example, it returns each of the pages based on the document's bytes being provided to it. It'll then loop through each of the page images and convert it to a base 64 encoded string, which we can then include in the user content for the GPT-4o request. And because we're working in that the realms of using GPT-4o and structured outputs, the system prompt is fairly straightforward, and we're just providing the user content here. Again, the response format. But here I also want to point out the enablement of log probabilities, and I will come back to the reason why I've enabled that when we look at the extraction itself. So with this specific example, we're seeing a much higher result in accuracy. But because we're not working with document intelligence now, how do we calculate the confidence? This is where log probabilities comes in. So Azure OpenAI's API in a request to GPT-4o can provide the probabilities for each token that it generates. And we can use this to our advantage. If we tokenize the output that's provided by GPT-4o for our structured object, and we find all of the tokens that are associated with a generated value in the log probs output, we can then determine the confidence of that specific field. And this gives us that confidence score. So you can see in some examples where the confidence is so high that it's 100% certain that it's extracted this specific value exactly as it is. But you can see here that there's also a few pieces of information that weren't inferred very well, like that renewal due date. And it's inferred that the last day of the the policy itself is when the renewal is actually due. So it didn't quite pick up what we were looking for. So how can we resolve that problem? How about we combine both of these techniques together? So combine the best of both worlds for a comprehensive extraction. So we take the Azure AI Document Intelligence Markdown, we take the Azure OpenAI GPT-4o Vision, which we've seen is more accurate than the other approaches, and combine them together. If we scroll down to where we actually create the request, it's as simple as it was before. So we extract the data from Document Intelligence as a markdown response. We create exactly the same extraction prompt for the user prompt for this insurance policy. But now we also provide the markdown content as well as the images from each page. So here we can analyze the visual element of each page using GPT-4o, but we're also providing the specific text just in case there is something in the text which the vision processing cannot determine. And again, we make the request with the log probabilities. In this specific example, obviously, we're using Azure AI Document Intelligence. So here is the representation of the markdown, and it's extracted all of the text. Because we're working with quite a digitized document already, the text here is quite easy to extract. So some of the information that was missing in the vision extraction, so say, for example, the policy holder's driving license number, it didn't get that quite correct. It missed one of the one of the characters in the output. Because we're providing the text now, that text does include that, which means that when the model is processing the data, it's got both of these values, both the vision capable output as well as the text-based output to lean on. So this is quite a long document, so let me scroll faster to where we do the extraction. So with this specific example, it's much more confident that the output is correct. And it's also even more accurate than the previous approach was as well. But one of the challenges you have with this specific technique, and all of these techniques, to be fair, is that you are bound by the context window for the language model that you're using. For most models today, this is around 128K, which is fairly large. But when you're working with vision-based scenarios or large quantities of text, if we think about the vision scenario first, an example of an A4 image is, it roughly converts to about 1,020 tokens with GPT-4o, but each model that processes images does it in a different way, which if you're thinking about that 128K, you've probably got about 100 pages that you can comfortably process in a single request. When you start combining that with text also, maybe you're looking at, say, 50 to 60 pages comfortably, because the text takes up quite a few tokens as well. So I'm going to shift gears and we're going to take a look at classification. So classification is a technique that is required if you're processing multiple types of documents. It's a way that you can first analyze the document, determine what it is that you're processing, and then move on to a data extraction technique. So say, for example, we had two documents. One was an invoice, one was this insurance policy, but this AI system has no idea what either of those documents are. You don't even know what either of these documents are, and you're allowing the system to process them. You first need to classify. So the first technique we're going to look at takes advantage of the understanding of the RAG pattern for finding relevant context for chatbots. And we can apply this same logic to determining if the content of a given page or document is semantically similar to a specific classification. So first, what we need to do is define a set of classifications with relevant keywords. We create embeddings for them. We then analyze the document to get the text, and in this case, we're using document intelligence again. We then embed the content of each page, or you could embed the entire content of the document. And then we'll use cosine similarity to compare how similar each of the classifications are to the content of the page using their vector representations. So let's have a look how this actually works. So in the classifications, we're setting up again the same expected outputs, what we're expecting for each page, having gone through manually. We're working with the insurance policy document here, and we're breaking it down by page. So we're expecting that the first 5 pages are insurance policy, the 5th page is an insurance certificate, and then the rest of the pages are terms and conditions. We can define our classifications, and really these can be anything that you're trying to classify. This becomes almost, instead of building a classification model that visualizes what a document is and then can tell you what the classification of that document is, instead we're defining it in natural language. Because I'm working with pages and not documents, in this specific example, I'm saying there's an insurance policy, here's a description for it, and a few keywords. Those keywords are going to be really useful when we create the embeddings to do the similarity. An insurance certificate and the terms and conditions. Again, we follow those same steps as we did in previous examples. We convert the document to Markdown. In this specific example, once we've also converted it into Markdown, I need to get the representation for each page. So I take the data from each page from the analysis result. I then create the embeddings. So I convert the classifications to embeddings for each of the keywords. And then I also convert each page to embeddings too. Then we classify the pages. So this is where we use the cosine similarity. So for those not aware, cosine similarity is a metric that's used to measure how similar 2 vectors are. The embeddings that we have are a numerical representation of the text that contain the semantic meaning. So by converting the document and the classification to embeddings, we can compare them, the similarity between them. When the similarity score is close to 1, this indicates that we can that the 2 pieces of text share similar characteristics, while something that's closer to 0 or a negative value indicates that it's further away and that they are not similar. You have to find then the best match. So we go through each of the classifications for each page, and we determine what the best match is. And if it's above a certain threshold that we can define, that provides us that confidence that it's highly classified. So if we take a look at the extraction itself, so once we've compared the accuracy, you can see the results here. So the accuracy is quite high, 92%. And you can see here with our confidence, the similarity score in this specific example. What I've done in this demo is also showing you what the matches are to all the other types of classification, not just the one that it's picked. But you can see that it's quite accurate, but you can also see that the similarity between the keywords it's not high. We're looking at between 50 and 60% confidence, some as low as 39% there, which is why it wasn't classified, because I set the threshold to 40%. But you want that threshold to be a lot higher. So to adopt this technique, you need to start implementing different ways, different keywords that are specific to the types of documents that you're extracting, and tailor the technique to your specific use case. Jumping into using completely GPT for this classification technique, we can actually adopt the same process for GPT with vision that we demonstrated for extraction to also do classification. So we take the document, we convert it to images, and then we along with the classification prompts in text, in natural language, we prompt GPT-4o to extract the classifications for each page. Again, the similarity is the expected output's the same, the ground truth is the same, and the classifications are the same in this example. But in this specific example, we're going to use all of the classification data in the request to GPT-4o, not just the keywords. So again, we take the classifications, we add them to the user content, we convert the page, the document into images and add them as base64 strings, and then we make a request. Here again, we're using prompt engineering techniques, use the classification provided, classify each page of the following document into one of the classifications. If a page contains multiple classifications, choose the most relevant. And if a page doesn't fit, use the classification unclassified. So we're trying to mimic the same technique that we were demonstrating with the embeddings. But here it's going to be completely language model driven. And to get the confidence scores or the similarity scores, instead of asking the model itself to provide a percentage or a similarity, what we're actually going to do is use that same log probability technique to check how confident it is that the model created the right token based on the expected output. And we're using structured objects here. So you can use structured objects again for this specific technique, so that the output that you get is in an expected format. Now, we are getting 100% accuracy here, but what I want to caveat with everything that I've shown you is that this all depends on your type of document and the way that you prompted it. So we're seeing high accuracy here, and we're seeing high confidence. But there is one key challenge with this particular approach, specifically if you're classifying with vision, and then subsequently you're going to extract with vision 2, because you're processing the page, the document, multiple times, which can be less cost effective than using prompt engineering techniques to both classify and extract in the same request. So you may be able to incorporate both of these changes, the classification and the extraction, into one request. When you're working with a single document classification, it may also be possible to only really use the first few pages. So if you're trying to work out if a document is an insurance policy or if it's an invoice, what you can do is just use the first few pages to perform the classification rather than the entire document. And that's really cost effective when you're working with, say, a 100+ page document where you don't want to be processing that much data. Cool. So let's jump back into the slides. There's a lot to take in there. So now that you've seen everything in action, I want to bring everything back together so that you understand a bit more about what we've looked at today. So if we look back at the complexities that we started with, extracting data from documents is challenging due to the wide variability in document layouts and structures, as well as specific domain jargon. Traditional vision models need to understand the nuances between accurately extracting with a large training data set, while language models, they need guided instruction to work effectively. And while structured data is relatively straightforward to extract with simple prompting, unstructured data requires some investment in prompt engineering to ensure that high accuracy. Additionally, building AI automated systems require true confidence from the model, and it needs to come from the model's own internal assessment to validate whether it is working effectively and when to escalate to a human. From the techniques that we've explored, we learned that Azure AI services provide a powerful set of tools that can be used individually or together to create an effective document classification and extraction pipeline. We can take advantage of Azure AI Document Intelligence, not only to perform the OCR layout analysis of documents, but to also provide bounding boxes and confidence scores that we can use to help with the human review if required. Combined with language models for classification and extraction, we can improve the overall accuracy too, reducing the need for extensive custom model development. And even going one step further and leveraging multimodal models with vision capabilities can further enhance the accuracy, where the model can truly see the document and analyze it, including images and diagrams, as well as signatures and check marks. Each technique that we explored today provide their own benefits and drawbacks, and it's important that you carefully evaluate each of their performance and limitations to optimize your own document processing at scale. The balancing act is essential to ensure that you build a highly accurate, timely, and cost-effective solution. And while we've observed that with these scenarios that language models can greatly improve the accuracy and speed for document processing, I need you to take away from this session that there is no one-size-fits-all solution. That's why I showed you the combinations, as you might find that one of them works better than another. It's important to evaluate all of the services, all of the techniques that you have available to you to find a solution that actually works for your needs. Thanks everyone for joining to learn more about document processing techniques. You can find more detail on the work that myself and the startups team have been doing in this space with the link on the screen. There's a QR code there for you to scan as well. You'll find all of the samples that I covered today for testing your own scenarios, as well as a range of articles that discuss in detail how each of these techniques work, as well as an in-depth evaluation analysis for each of the techniques you've seen today. So you'll find the cost analysis, the accuracy, the speed. And yeah, let's take some questions. Has anyone tried these approaches before? Do you see potential improvements or other effective techniques that you've explored? I'd love to hear some thoughts.
Yeah, great. We have some question I will share with you on the screen. The first question is from Martin.
What challenges do we have when processing Danish language documents? So a lot of the GPT models are able to process in other languages, but what I found when extracting data is that if you extract in English, I'm not saying to only use English, but if you extract in English, but the document is in another language, you'll find that the extraction still works really well because it's translating the text and the document into your expected structured output. But you can also get highly effective extraction by also providing the prompts in Danish as well, in other languages.
And the next question from, again, Martin.
Can we have control over the LLM? Yes. So although I've demonstrated today using GPT 4.0 and 5.3.5, evaluate the models as well. The technique itself applies to any language model. What I was just demonstrating today was within the capabilities of Azure. So 100% you could explore another language model from Anthropic.
And the Gabriel question.
Can we extract images from the document? Yes. So if you want to extract the actual image, Azure AI Document Intelligence in the layout analysis is really good at this. So it will bring back the image itself, so you can do something with it. Because you're then working with a language model like GPT 4.0, which if you're using the vision capabilities, you can do things with the image, like explain what the image is or extract data from the image. So say you had a chart or some kind of table or diagram within the document, you can actually extract data from that too, even though it's an image.
Okay.
Are we sharing our data such as documents with OpenAI during the processing? So with Azure OpenAI, you are providing the document for extraction, but the model and the the API are stateless, so they do not store your document anywhere. There are some. There is a. I can share a link also around the privacy policy that we have around Azure OpenAI, because we do have a moderation step where some data will get stored if there is if this is a detection that there's content moderation that needs to happen. So say, for example, it's harmful content. But other than that, the answer is no. I think this question is also covered by the last answer.
Yeah.
So yeah. Are there any cost-saving strategies when using Azure AI for large document scale processing, such as batch processing or custom models? Well, it's quite interesting because the GPT with Vision approach, if you're processing large documents in large quantity, it's actually more cost effective to use the Vision capability to extract data. And because it's highly accurate and highly confident, there's high confidence, you'll find that you'll just naturally have a higher cost saving using that approach compared to some of the other techniques. Can we pass the image link in blob storage instead of passing base 64? I'm not sure. I'd have to go away and find an answer to that. As far as I'm aware, it's just an image URI. So you should be able to provide, if it's publicly accessible, you should be able to just provide a URL. But I can't guarantee that, and I need to look that up.
Okay, I think there is no one question is about can we get a recording of the session? Yes, that we updated, uploaded on our YouTube channel. I will send our YouTube channel link in the chat. You can watch after that the end of this session. And thank you again. I think there is no more question. Let me check more. Yeah, and the other comment is thank you for your great presentation.
Sure,
And
thanks.
yeah, thank you very much again. If there is no more question, we can close this session.
All right.
Okay, James. Thank you very much again. Have a good day,
Cool.
guys.
Cheers, everyone. Thank you.
Bye.